I believe that good 3D resolution is similar to what we consider good resolution in 2D. Both the left eye and right eye image should have the same kind of resolution that we expect out of a 2D image. I'm proposing that we look at 3D as two 2D images, one obviously for the left eye and one for the right eye. Now, to further expand on that and to amplify, to give you an idea of how do we evaluate 2D resolution and therefore 3D resolution, we need to be looking in the picture at how well it handles horizontal information, how well it handles vertical information, and how well it handles a combination of vertical and horizontal information. That when you look at images, the picket fence is this direction, there's lots of information in this direction, and if you look at the detail that goes into someone's skin, that's a combination of vertical and horizontal resolution. So we need to evaluate all three. Even though it's vertical and horizontal, we actually need to evaluate each individually and then evaluate the two together. First of all, it's a flat panel display, and the flat panel display can't do any better in 3D than it can in 2D. So one of the things that I'm asking people to look at is first look at the 2D capability of the panel. And I'm asking them to look at it from two different perspectives. Number one, it can't do any better in 3D than it can in 2D. Number two, the majority of content of what you're going to be watching for the next few years is still going to be 2D. So it's important to know what a set can do in 2D from the point of view it's the foundation of the set's ability to do 3D, but it's also the majority of what you're going to be watching. That in an active system, we have shuttered glasses that flash in front of our eyes. In the display in an active system, what we do is we deliver a full resolution, high definition image for the left eye to the display device, and the glasses open up the left side so that the light from the left image comes to the left eye. And then, of course, it shuts off the left side, and the next image that comes up on the screen comes to the right eye. So it's something that we call sequential, where the left eye and right eye come one after the other. Now, the brain has a tremendous ability to retain images so that it actually sees both images as being present at the same time. And of course, we can speed the rate up to a point where there is a total belief that you're seeing both left eye and right eye simultaneously. In the passive system, we have a single display, and we actually have to show both the left and the right image at the same time. Since the display is limited in its resolution capability, we literally have to cut each image in half. The vertical resolution of the image is cut in half, and we have to do that in order to get both the left eye and the right eye on the screen at the same time. It's not an accurate claim by the criteria that I'm applying to judging whether it's real or not real. And of course, again, as a reminder, the criteria I'm applying is looking at each half of the image, the left eye, the right eye, looking at each image as a full 2D image. So what I'm doing to show that I can't justify their claims, or I cannot support their claims, is I'm putting in two full resolution images, one for the left eye and one for the right eye. when those images are displayed in the 3D mode on the flat panel display, it's obvious that half of the vertical resolution is gone. There is no mistaking that it is gone. Therefore, I can't begin to support their claims that the two halves make a full image. It doesn't, and it's easy to illustrate that it doesn't. Now, this could easily narrow the vertical resolution of the display, in other words, further compromise the resolution of the display. And it most certainly is going to compromise the resolution of the display because the filter is a distance away from the display itself. So if you're looking down from a vertical angle or up at an angle, then the filter is not going to line up exactly with the lines in the picture. In fact, even from a fixed position, when you're looking up at the top of the screen or down at the bottom of the screen versus the middle of the screen, what you see is going to be different. Now, at minimum, this is going to severely narrow the vertical angle at which you can see a 3D image. And of course, it's going to interfere with the 2D image. It's going to interfere with the vertical resolution of the 2D image. And once again, I'm making a point of the fact that you watch 2D at least as much as you're watching 3D. Therefore, what that filter does to the 2D image, in addition to what it does to the 3D image, is of critical concern. I actually believe that the glasses are going to be a small part, an almost insignificant part in the contribution of fatigue factor when compared to the potential or the possibility of things going on in the 3D image itself. So that the depth of the 3D image and the things that are done in 3D are potentially going to cause a much greater fatigue factor on the part of the viewer than either the active or the passive glasses.
Thank you very much for sharing your perspective. Now that you've told us about your observations, can you show us a bit how you arrived at them?
That's the big part, and I would really like to do that. So the pixel phase test pattern is testing both horizontal and vertical resolution at the same time. In the two bars above this one, we have 2 pixel transitions. So if we go in this direction, it takes 2 pixels to get from light to dark. And the same for the horizontal direction. So this represents half system resolution, where this one represents full system resolution, and then the 3 that are down here at the bottom represent 1/3 system resolution because it takes 3 pixels to get from light to dark. So this is 1/3 system resolution, this is 1/2 system resolution, and this is full system resolution. Now, we come over to the passive 3D display, where we know that vertical resolution is going to be gone. Now, this particular pixel phase test pattern is what's known as 3D flat. In other words, the left and right eye exactly match each other. This is the best possible scenario for a passive display to show resolution. And of course, as you can see, the resolution is completely gone. In the pixel phase pattern, we looked at horizontal and vertical information simultaneously. Now what we want to do is look at each independently. And we're going to use the SMPTE RP133 test pattern for that. And it is in a 3D flat mode, meaning the left eye and right eye are exactly the same. Once again, this is the best possible scenario for a passive display. In the active display, it's clear that there is both horizontal and vertical resolution right up to single pixel transitions. Here we have single pixel transitions in the horizontal direction, and here we have single pixel transitions in the vertical direction. If we go over to the passive display, what we see is there's very little horizontal information and absolutely no vertical information. So what we want to look at is what does the resolution look like in 3D. Here, if we look at the active display, we can see the second image is at full resolution. When we go over to the passive display, we can clearly see that the second half of the image is being filtered out. You can see that half of the image is missing. So this is an illustration of the fact that when the image is in true 3D, when there's dimension forward and back, that we don't have as much resolution in the image as we do when the image is flat. Now, in the active display, we have full resolution, and when we have full vertical resolution, along here in the diagonal, you can see that we have a very smooth line. Also, note the top of the circle. You can see that the circle is a smooth circle because we have equal resolution in both the horizontal and vertical direction. Therefore, a circle can be perfectly smooth. Now, as we move over to the passive display and we look at the same area, if you look along the diagonal line, you can see that it's quite jagged because half of the vertical information is missing. Therefore, it's not possible to create a smooth diagonal line. You see that also in the circle where the vertical information is missing. Here, the jaggedness of the edges is more apparent than it is in the diagonal line because of the shallow part of the circle. Now that you've seen the kinds of errors we're seeing in test patterns, it's going to be easier for you to spot the same kinds of errors in real picture information.